Alright folks, let's wrap this sound unit up. First and foremost, about beat frequencies. If you've got a couple of sources that differ by 15 hertz or less, then a beat is produced. Now, by 15 hertz or less, it's basically just what the human ear can perceive. The beat frequency will actually be the difference between those two sources, and it's an absolute value. You're not going to get a negative beat frequency. So that means if they differ by 15 hertz, I would hear a beat 15 times per second. That's the wah 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 sounds. If they differ by more than 15 hertz, then you'll probably just hear them as separate tones in general. So to look at that, I've got a little simulation up here. Let's say I've got two sources that are both 250 hertz. So if I play that sound, then it pretty much just sounds like a single tone. Because if you line the waves up, then you're getting constant constructive interference pretty much. But if I change this one to, let's say, 257, you start to hear a crazy phenomenon of beats not quite lining up. Now the reason for that, if you look at them on top of each other, is one wave has a slightly longer wavelength and they slowly get out of phase. Then they destructively interfere for a bit. Then they slowly get back in phase. Now how quickly or how slowly they get out of and into phase depends on the difference between their frequencies. The more similar they are, the longer it takes. The farther apart they are, the more often it happens per second. So that's the deal with beat frequency. Super useful if you're trying to tune instruments. Let's say you want to get a guitar in tune with itself, but you didn't bring your tuner with you. All you got to do is play the same note on two different strings, and if you hear a beat, they're not in tune. Tighten or loosen, see if the beat frequency increases or decreases. If it decreases, you're going the right way, and once you get it so there's no beat frequency, you are in tune. Brilliant! The last little bit I want to talk to you about in this sound unit is the Doppler effect. So, the Doppler effect, to think of it, you all have experienced it before. Every time you've heard a car speed past you. So what sound does it make? It makes roughly this sound. So it sounds like a higher frequency, and then it goes to a lower frequency after it passes you. Now the reason is actually a change in frequency. Pitch and frequency are pretty much the same thing. Now the car's sound wave is not actually changing as it passes you. You are all very special individuals, but you're not so special that sound waves change when they see you, necessarily. So what's going on here? Well, I've got another little simulation up here about the Doppler effect. In this simulation, I've got, I guess it looks like a planet giving off some sort of a signal. So a series of green and yellow sound waves are going away from this central planet basically in a circular shape or a spherical shape. The waves are going off in all directions. Now there's a spaceship that's collecting these sound waves, and you can see what the spaceship is observing in the lower left of the simulation. When it gets hit by a green wave, they're counting that as a crest, a yellow wave as a trough. So it's passing by crest to trough, and its wavelength is how quickly this spaceship identifies it. So if the source approaches the spaceship, it's still giving off these circular patterns, but now with it heading to the left, as it gives off the circular patterns, to the left of the planet, they start to bunch up, these sound waves. And to the right, they're more spread out. That's the Doppler effect. So the spaceship is experiencing a lot more crests and troughs as the planet's heading toward it, because all those crests and troughs are bundled together. After the planet has passed by, the spaceship experiences it less often, so a longer wavelength means a lower frequency. If I reset this thing, I get a similar effect if, let's say, the observer approaches instead of the planet. Now the observer is hitting each wavefront more often than it would if it was just sitting still, even though the wave itself hasn't changed. According to the observer, it's a much lower wavelength, higher frequency. After it passes the planet, same sort of deal. Now it's traveling in the same direction as the wave it's encountering, so the wave is hitting it less and less and less often. So you're getting a really big wavelength, really low frequency. So what ultimately matters to determine the frequency that's heard versus the frequency that's emitted is the source speed, the observer's speed, the wave's speed, because if the pulses are coming off faster or slower, that's going to make a difference too, and the frequency that's actually emitted. So here's another little picture of it. There's a small child. He looks like he's very unconcerned that a driverless police car is heading toward him, but as he hears these, he's hearing a much higher frequency because the police car is bundling up those wavelengths in front of it, and she is hearing a much lower frequency. So the Doppler equation just comes down to this. The observed frequency equals the wave, well, okay, let me just list the equation all at once. F observed equals, in parentheses, you've got a fraction. The numerator is V minus VO. The denominator is V minus Vs. That entire fraction is multiplied by the frequency of the source. So V is the speed of the wave. That'll be in meters per second. Vs is the speed of the source. That'll be in meters per second. VO is the speed of the observer, also in meters per second. Fs is the frequency of the source in hertz. And Fo is the frequency the observer hears or detects. This doesn't only work with sound, this is working with light as well. For this reason, on the red end of the spectrum, that is a higher wavelength, lower frequency for visible light, and on the violet, the purple end of the spectrum, that is a low wavelength, high frequency wave. So they call the Doppler effect, they'll call it redshifting if the wave seems to be spreading out and getting longer. They call it blue shifting because the blue-purple end of the spectrum is where it seems to bunch up. So redshift means a higher wavelength, lower frequency for both sound and light. Blue shift means a lower wavelength and a higher frequency. Cool. So with this equation, just ask yourself what's moving. Is the wave moving? The answer will almost always be yes. Is the observer moving? If no, that's 0 meters per second. Is the source moving? If no, that's 0 meters per second. So make sure that with this equation, it just has a bunch of variables, but it's fairly simple to work through. The one issue that you might run into with this equation is when to use a positive number, when to use a negative number. So once you've identified who the observer is, the direction that the wave is traveling, sound or light, when it hits them, that is all of a sudden considered the positive direction. So I could also put together another equation. Let's say if the observer is listening to some waves that are heading to the left, then all of a sudden the left would be the positive direction. Once you identify the positive direction, ask if the observer is heading in the positive or negative direction, and if the source is heading in the positive or negative direction. Once you've got your positives and negatives all figured out, slap it into the equation, and you'll figure out the actual frequency values. All right, that is it. Take it easy.